So we've looked at linear applications. What we're going to do is also look at quadratic applications and exponential applications. Now, if you haven't heard those terms, quadratic and exponential, before, that is completely fine. What we're going to do is heavily rely on the graphs of these equations and getting the information from the graphs in order to solve, because there are certainly skills for solving quadratic equations and exponential equations, but they just go a little bit beyond what we're covering in Math 95. So what we're going to do is kind of simplify it, and I'm going to show you how to use Desmos in particular, this online graphing calculator, to solve these values, and we're going to kind of skip solving algebraically. It's going to be more about interpreting what we're seeing on these graphs. So, quadratic. Quadratic has a general form, and this might work. There we go. When we write a general form for a quadratic equation, it looks like this. The key piece that's showing up in there, so A, B, and C could just be any number, but we need x squared in there. It's the x squared that makes it quadratic. So if we look at this example with the toy rocket being shot up in the air, and we're looking at its height after a certain amount of time, if we look at the equation, the fact that there's that x squared in there, and that there's no exponent larger than the exponent of 2, so if we had an x cubed in there, that would turn it into something else. But the x squared is what makes it quadratic. So, when we graph something that's quadratic, it looks like this. The shape is called a parabola. And what usually happens is it either reaches some maximum value and then goes back down, and there's this nice symmetry to it. If you cut in the middle there, it's symmetric on both sides. Another form is that it can look like this, where it's opening upward. So it would be that it reaches a minimum value and then increases back up. So with this case, what we're doing here is we're mapping the height of this rocket. So it's like we're launching the rocket here, so we're at 0, 0, so time hasn't started and we don't have any height. As we move along the x-axis, time is passing, so here's like 0.5 seconds, 1 second, 1.5 seconds. So it's like the stopwatch is counting as we go in this direction. And then what we're tracing is the height of the rocket. So this looks like a rocket launch here because the height's growing, 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 but eventually it's going to hit some maximum height, and then it's going to head back to the ground. So, when does the rocket reach the ground? So, with this, if we think in terms of our variables, where y is mapping height, and x is mapping time, then what we're looking for here is a height of 0. So we're looking for when is y equal to 0. So we're just going to look for those cases, and where that should be coming up is we have here at 0, 0 and 3, 0. So we have two coordinates that work here. In fact, let me write this down, 0, 0 and 3, 0. However, that 0, 0 isn't necessarily it reaching the ground. It's kind of starting from the ground at that point. So I actually don't want to use that 0, 0 because it doesn't quite match the wording of the question. So it's this 3, 0 that I want to work with here. So it has a height of 0, and then we have that x value of 3, which is the amount of time that has passed in seconds. So when does the rocket reach the ground? After 3 seconds. So with this, the idea is that the visual of the ground is along the x-axis. That's the ground with a height of 0. When does the rocket reach 32 feet? So with this one, we're setting our height, which is y, equal to 32. And how we can visualize this is as a horizontal line, kind of like I just drew down here, where that's a height of 0 going across the bottom there. So what I could do is pick up that line and now visualize it up at 32. So find that height of 32 and draw a horizontal line. And we want to find all of the points that intersect with it. So we've been working a lot with linear equations, and there's only one intersection. when we did a problem like this. But with the quadratic, because of this curvature to it, we can have two intersection points. So I'm looking at this 132 and 232. So I have these two coordinates, 132 and 232. And what this represents is two moments in time where we have this height of 32, which makes sense with this rocket being launched into the air because it's going to pass going upward past that 32 feet, and then it's going to turn and come back down and hit that height of 32 feet again. So there's two solutions to this. It's going to reach that height of 32 feet after 1 second and 2 seconds. And our last one here is, what is the maximum height the rocket will reach and when does it occur? So with these quadratic applications, we often talk about maximum and minimum values, and that's coming through a point that's called the vertex of it. So like I mentioned with this one, we can see it coming through as a maximum because this parabola is opening downward. If we had a case like I drew up here, that would be representing a minimum value because it's opening upward, so it's reaching this lowest y value and then going back up again. So we're using this coordinate 1.5, 36. So just to keep it straight, 1.5 is representing time, where 36 is the height. So what this means is that after 1.5 seconds, the rocket will reach a maximum height of 36 feet. So when you look in terms of the y-axis, if that's all of our heights, that's the highest height that it will reach. That maximum height. You won't see any other y values that are larger than 36 for this graph, since it turns around at that point. Alright, so with this one we didn't really need to use a calculator at all, even though we had the equation here. Like some of this we could have solved for algebraically. However, let's look at a case where, what if we don't have the picture? How can we create the picture and find these kind of same values of looking for different x coordinates, y coordinates, or these minimum maximum values? So we're going to have a rock is thrown into the air off of a cliff and travels upward before turning around, falling into the ocean. So if we want kind of a visual here, let's see, we're on a cliff and we'll have our person there and we're going to have the ocean down below. And what we're going to do is throw a rock. So it's going to go up, turn back down, and then hit the ocean there. So we're seeing this parabola coming through. We're going to see the same kind of opening downward, so we'll have some maximum value occurring. The idea is that we'll have some height that we can map as time is passing after throwing that rock. Now, they give us the formula right here. So what we're going to do is go to Desmos, because what we're going to do is look at two cases. How long does it take for the rock to hit the water? So what we're asking for is we want to find t. So we don't know what t is, but this idea of the rock hitting the water, that would be a height of 0. So we're going to know what our output should be. We just need to figure out what our input should be. And then we're going to look for the maximum. So we're going to look at that vertex of the graph and grab the coordinate there. So let's pop over to Desmos. And let's see, I just need to memorize that formula real quick. So negative 4.9t squared plus 10t plus 50. Alright, when you have your variables in Desmos, you always want to work in terms of x and y. It's same for any graphing calculator. So no matter what variables you're using, you'll translate it back to input and output in terms of x and y. So this is the Desmos graphing calculator, and it's going to be really helpful here for when we look at this example, because it can show these key coordinates really clearly. So we had negative 4.9 t squared, but I need to change that to x squared, and then it was plus 10x plus 50. Now, I'm off the screen here. However, I could answer my question about it hitting the ground. What I could do is I could zoom out with my mouse. I know I need to see at least up to 50. So this is doing all right here. If you want, you can adjust the scale of the window if you want to. Really, this graph, you can see it kind of highlights some key coordinates here, and that's really all we're going to use. So here we can see our coordinate 0, 50, which is the idea of us standing on that 50-foot cliff. And then we launch the rock upwards. It's going to hit a maximum value, and then it's going to come back to the water. So it highlights those key points, and that's really what we're going to focus on in this class. If the window is not working for you, what you can do is, I'm sorry, it's a little bit off of the recording screen that I have here, but in this upper right-hand corner, there's this wrench that says Graph Settings. And what you can do is play around with the window, like set your x-axis. Like maybe I look at this and see, I only really need to see from like negative 5 to 10. So what you could do is edit there. Sorry, this is kind of turning into a Desmos tutorial, but it is very helpful in terms of graphing. And that just makes the graph so much clearer. I don't have as much empty space. If you need to adjust the y-axis, like say this was still going off the page, then you can adjust those pieces there. So if you need to adjust the window, you'll be working in there. All right, so our first question was when it was going to reach the water again. So again here, I am standing on that cliff 50 feet high, launch the rock up, and it comes back down. And then that water is that height of 0, and that's where we're crossing the x-axis. So I have this t equals 4.374. So let's go ahead and write that down. 4.374. Alright, so in terms of answering the question, how long does it take for the rock to hit the water? It will take 4.374, and our units for time is in seconds. Where that's kind of hidden in there is they describe this velocity 10 meters per second. So that's where I'm grabbing my units for time passing. It also makes sense if you throw a rock off the cliff, you're not going to be waiting like 4 minutes for it to come. You'd have to throw it very hard and very far for that to happen. Seconds makes more sense in terms of time passing here. Alright, the maximum. So let's go back to Desmos. And I want to use this vertex, which Desmos kindly highlights for us. So you can see it's kind of a grayed out circle there. If you just click on it, it sets the sets the value so you can see it clearly. So 1.02 and 55.102. So our vertex 1.02 and 55.102. So we have time. So that's in seconds. We have height, which were all of our height measurements, which is kind of coming through there. Also there is all in meters. So we could say after 1.02 seconds, the rock will reach a maximum height of 55.102 meters. Alright, so those are quadratic applications there. It's going to be some sort of graph that has an arc, like kind of an arc to it, but really it's coming down to a parabola. And if you look in the equation itself, you're seeing our input variable squared in there, and that's what makes it quadratic. But some types of questions we can look for are these input values, output values, and vertex. Again, maybe you've learned how to do these algebraically, and if you want to solve them algebraically, that's fine, but in terms of expectations for this class, it's going to be more about either reading from a graph like we did up above here, or plugging into Desmos and grabbing those key coordinates there. And to just show quickly one more case that we could deal with that we talked about here, like that idea of drawing a horizontal line at 32 and finding those coordinates. Like let's say with this case, I'll be above, we'll be above 50 meters there. Let's say we wanted to see when the height would be 32 meters. If we look at the graph, you can kind of visualize 32, but it's going to be tough to grab those points there on the graph. It's not kind of these special coordinates that Desmos highlights for us. And you could kind of drag along the graph and try to get as close as possible, but that's really hard too. So what we can do is actually graph a horizontal line. So say I wanted to graph a horizontal line of 32. Now if I just type in 32, that's not going to do anything. Really what I want to type in is the line y equals 32. So I'm going to do is edit that and go y equals, and then you can see this horizontal line, and now we have these great coordinates for where we're intersecting. So we can see, okay, negative time doesn't work for us, but after 3.192 seconds, we'll be at 32 meters high. So if they give you an output value, you'll just draw a horizontal line within Desmos with y equals whatever that number is, and look for those intersection points.